Hello everyone, you're watching Neri Chem. This is question 4 of the HSC 2018 paper. Which of the following greatly enhanced scientific understanding of the effects of trace elements? So we have improved filtration techniques. So the first thing I would say about improved filtration techniques is that filtration is a mechanical process. So let's imagine that I take a blue color and I draw a flow of liquid. Now, below I will draw what could just be a cloth. It could also be coffee filter paper. And in the flow of liquid, I will draw black dots, which represent a solid which is undissolved in the liquid. Now, filtration is just simply separation of solids, which can either be in liquids, but we could also talk about filtration when it comes to gases. I'll just talk about solid-liquid separation. Now, the flow which goes through the paper is just the liquid, and therefore the solids are retained on the filter paper. Now, this is just a mechanical process because the solids cannot go through the filter. So when we talk about the history of science and the filtration techniques, well, we can see that although filtration could probably be enhanced through scientific understanding, in the end it's just a bit of a basic process which probably has not likely influenced the understanding of the effects of trace elements. However, if we were to talk about separation techniques, then I would say that the question would be altogether slightly different. I'm going to draw a Venn diagram. Here are separation techniques. And inside the Venn diagram, here I would say is filtration. So what I mean to say is not all separation techniques include filtration, but all filtrations are separation techniques. And separation techniques would definitely have enhanced the scientific understanding of the effects of trace elements, because when we look at the history of the discovery of all the elements on the periodic table, we see that, for example, cesium, which was discovered in Germany by taking huge amounts of mineral water from spas, which had to be then separated, filtered, separated, and a series of long extractions in order to get just a tiny bit of cesium. Well, then we can study the cesium which has been extracted, and it's thanks to those separation techniques. But I would say it's not A, because filtration is a basic process which, although it has developed, it cannot be the answer. The development of atomic absorption spectroscopy. This is the correct answer. Why? Well, let's think about atomic absorption spectroscopy and what it can do. It's sensitive. So let's go back to my example on cesium. Cesium was, thanks to atomic absorption spectroscopy, discovered. How was it discovered? Well, I'm going to draw a light bulb here, which just represents a source of light. And I have 3 beams in red and 1 beam in blue. Now, in black, I will draw single atoms of cesium. And below, I will draw a flame, which has produced these single atoms of cesium. Now, the fact that they're single atoms is really important. I'll explain that. What happens is, the atoms will absorb only a very specific wavelength of light. And the blue line that we saw before is missing. What happens? Cesium has atomic energy levels, and those atomic energy levels are what are called quantized. They are only a very specific value of energy. And that blue light is absorbed, in this case, by cesium. So we can tell that we have cesium in a sample when we detect the light, which is absorbed by a particular atom, and that is how cesium was discovered. The reason why these need to be single atoms is because cesium in the bulk state looks just metallic, and it would have the same, pretty much the same visual characteristics as sodium or potassium metal. A lump of sodium metal and a lump of potassium metal look pretty much indistinguishable. Of course, they are different elements, but why are they indistinguishable? Because they're metallic. So the single atoms have different properties to the bulk metal, whereas the orbitals in the atoms have quantized energy states which are particular and emit visible light. The bulk metallic state has valence bands, which basically means that all metals essentially look the same. Now, this is a sensitive technique. Why is it a sensitive technique? Well, because the human eye, on its own, is limited when it comes to trace elements, because we cannot detect such small quantities of light, and our eyes cannot tell us, our brain, what specific wavelength of light we are detecting. I know that a color is red, but I cannot measure the exact value with my eyes. I need something in order to measure that specific wavelength. And this is where atomic absorption spectroscopy is more sensitive, because it is a lot more precise and requires a much smaller quantity. I can only see cesium if it is in a large amount. If it is in trace element concentrations, I cannot possibly see it with my own eyes, and therefore B is the correct answer. But just for the sake of clarity, we'll go to C. Now, particle accelerators would enhance your understanding of trace elements, but it is not as likely to be the answer as it is B. Why? Well, the creation of new elements in particle accelerators only applies to extremely heavy elements, because they're the ones that you need particle accelerators in order to generate. So I'll give you one example. Francium is a group 1 element, so it's in the same group as sodium, potassium, etc. In order to generate francium, you take gold and you bombard it with oxygen. Now, oxygen would be 18. And then we create francium, which would have a weight of 209. And we create 6 neutrons as well. So there's 215 on the right. 215 minus 18 is 197. That means the atomic mass of gold and the atomic mass of oxygen is the same on the left as it is on the right hand side. So we know this equation is balanced. Now, francium is fantastic, but it is only one of a small number of elements which are extremely heavy. The question itself is talking about elements in the plural. So there are lots more elements which have been enhanced in their understanding by absorption spectroscopy than by particle accelerators. So actually B is more likely to be the answer than C, although C is not totally incorrect. Finally, the work of Le Chatelier, well, this is the easiest one to discard. Le Chatelier's principle refers only to reactions, right? So A plus B goes to C, or something of that style. When we're talking about enhancing the understanding of the effects of trace elements, we're talking a lot more about analytical chemistry, not about reaction equilibria. So that we know D cannot be the answer. Finally, just a comment, just a personal opinion I have about the tone of the question. When it says the effects of trace elements, it might just be the toxicologist in me, but this really does scream to me something about human health. Now, the effects of trace elements, probably the most popular thought which might come into someone's head would be mercury and lead. Now, we know that mercury, which is Hg, has effects on the nervous system at trace element quantities, and we know that lead can cause infertility at trace element quantities. And of course, you would need absorption spectroscopy in order to measure the effects of mercury and lead in your body, because very, 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 very small amounts of mercury can cause the effects I've just mentioned. So it's just a side note, it just screams human health. But anyway, I hope this has been helpful to you, and thank you very much for your time. I hope to see you next time. Goodbye.